I talked when I spoke earlier about why brittle failure in ceramics is particularly hard to understand and to predict, is that the grain structure in ceramics can be complex. There can be small grains, there can be large grains, there can be a combination of small and large grains, and that, with a combination of potential flaw sizes and flaw shapes, creates a great deal of difficulty in understanding the relationship between the flaw and the microstructure itself. The microstructure can really affect both the strength of the material as well as the fracture toughness of the material. So something I mentioned earlier, that the fracture toughness is typically low. The range of 2 to 10 megapascals per meter to the 3/2 covers a lot of the range of almost any ceramic you can think of, so that it means critical crack sizes are of the order of grain sizes, namely 10 to 50 micrometers. So small variations in microstructure, grain size, large variations in grain shape, and so forth can have a significant effect on both the strength and the fracture toughness of the material. In addition, crystal structures can differ widely from one material to another. I'll show a little later how this can affect the fracture behavior. And so things that we need to know are that microstructure will affect both the strength and the fracture toughness, but in different ways. Sometimes large grains are very useful for getting increased toughness, but can cause much lower strength. So that's why I say fracture toughness, measuring fracture toughness directly and assuming that will give you high strength can be a mistake. So let me move on and talk about first the effect of microstructure on fracture toughness. And I show a couple of microstructures here just as illustrations of how the microstructure can vary even widely within one given material. Here's a non-uniform microstructure of aluminum oxide that you see here. And let's show, for example, that the crack can extend over a large number of grains, as you see down here in the bottom, because it's in a region of fairly small grain size. So this microstructure in the same material will affect the behavior a lot differently than this flaw that might be up here, the extent of only 1 or 2 grains. So you have to be aware of that when you're analyzing your material and your microstructure, that even with one material, microstructures can vary widely. So in terms of how does the microstructure itself affect toughening, I will mention 4 different ways, 4 different mechanisms that have been put forth, and they apply to different materials in which there can be increased fracture toughness due to the particular effect of microstructure itself. Crack deflection, what is called microcracking, crack bridging, and phase transformations. And I will briefly go through each of these and kind of show how each of them works in its own way to change the toughness behavior. So here is this is work that Faber and Evans reported a number of years ago, what I call crack deflection. That is, ahead of the main crack, the crack path deviates due to the microstructure. It reaches some grain in which the crack path through that grain might not be preferable, so it changes direction, moves around that grain, reaches another grain, does the same thing, and the angle at which it moves will give rise to increased toughening depending on the particular material, the resistance of the boundary through which it moves, and so forth. Let me illustrate the effect of crack deflection in the following way. If I have grains with different aspect ratios, let me go back and show you. So here would be aluminum oxide with a very long aspect ratio grain. Here are some fairly equiax grains down in here. So as a crack might reach a large grain like this, it has to deviate from its original crack path by a large amount, as you see, to go around that grain, whereas going through the equiax smaller grain structure is much easier. And Faber and Evans were able to show that the fracture toughness increased with aspect ratio in a quantitative way, and their experiments were done on silicon nitride. So you can get somewhere 20 or 30% increase in fracture toughness just by changing the aspect ratio of the particular microstructure that you're looking at. One of the other mechanisms for toughening is termed microcracking. It also, Faber and Evans showed that there can be microcracking ahead of the main crack. Remember, there's a fairly high stress intensity field in the front of the primary crack, and that stress field can give rise to a number of small cracks forming, particularly grain boundaries, for example. And since the energy is absorbed by those cracks, there can be a reduction in the stress intensity factor in front of the crack, or there can be effects of the microcracking on the crack wake itself back in here, changing the local stress state behind the main crack tip. Some of the causes of microcracking: non-cubic materials, for example, have different thermal expansion coefficients in different crystallographic directions. So at large grain sizes, the stresses produced by thermal expansion anisotropy, which can be very large, can lead to spontaneous cracking. The other physical mechanism that can occur is elastic anisotropy. All crystal structures have differing elastic properties in different directions. The effect is much smaller than thermal expansion anisotropy, but still can give rise to changes in toughness values. And let me illustrate each of those in the following way. So this is effects of microcracking on toughness. In cubic materials, as you see down in here, the microcracking is independent of grain size. These are all cubic materials because the thermal expansion anisotropy is non-existent. When we go to non-cubic materials such as aluminum oxide, you can see that there's a very large effect of grain size because of that thermal expansion anisotropy. This is true of titanium oxide and niobium oxide as well. And even the stresses due to thermal expansion anisotropy are so great down in here that there's actually macroscopic spontaneous cracking where the specimens actually fall apart at large enough grain sizes. So I think if you go back and look, no dependence on grain size for materials, for cubic materials, a whole set of cubic materials, large dependence on grain size due to microcracking in aluminum oxide and other materials as well. I also want to talk about grain bridging. In grain bridging, the microstructure is such that there can be frictional interlocking between two sides of the crack that you see here. There can be what is called ligamentary bridging, where pieces of the crack differ maybe slightly from one another on each side of the crack, and each of those can give rise to some increase in toughness. You can see this example, probably, I don't know how well it shows up, but you can see what happens to an actual crack where there's bridging across this crack as this one large grain as you follow it through the microstructure. Those kind of mechanisms lead to what is called R-curve behavior, namely because the more grains that the crack passes through, the greater is the toughness. You can see here that the fracture toughness as a function of crack size increases with increasing crack size until it levels off at some point. So you see here that the fracture toughness goes from a value of around 3 to something around 6 point something, depending on whether you have relatively small cracks or macroscopic cracks. I would point out, though, that this does not necessarily mean that the strength of the material has gone up, because once failure has started from some of these small cracks and the crack is growing rapidly, there's been little evidence to show that it will slow down or stop just because it's moving into a region of greater toughness in a large size. These are 1,000 microns. It's a very large size crack, and probably failure has occurred well before this point would have occurred in a real part. But for controlled fracture experiments, you can see that microstructure has a strong effect on the actual fracture toughness of the material that I would measure with that size crack. And then finally, I want to talk a bit about transformation toughening, because transformation toughening is a popular way of toughening. Partially stabilized zirconia is the key material that's been looked at, and that transformations, in other words, from tetragonal to monoclinic in front of the crack tip, leads to different stress states here in the front of the crack tip, as well as some pinning action behind the crack tip, and both of those lead to fairly significant increases in fracture toughness, and those can, in most cases, lead to increases in strength as well. There are other kinds of phase transformations that can lead to toughening. An example here is barium titanate. At ambient temperatures, at room temperature, barium titanate is tetragonal and ferroelectric, and twinning can lead to increased toughness. You see through the peak in the curve here of critical fracture energy of barium titanate as a function of grain size. At elevated temperatures, where the phase transformation has taken it into cubic material, there is no dependence on grain size in here. So you can see, similar to the effect of thermal expansion anisotropy, this is a different kind of phase transformation than we saw previously, but all of these microstructural effects can have important implications for the toughness of your ceramic material. Let me move then into the effects of microstructure on strength and focus on the idea of large grains, because if a crack starts within a large grain rather than within the fine grain material, and I showed an example in aluminum oxide at the beginning of this section, the large grain itself can be the controlling factor in the strength of the material. And I will demonstrate that through the use of looking at examples of fracture of polycrystalline zinc selenide. I think you can see in this micrograph the polycrystalline zinc sulfide, most of the time zinc selenide contains large grains that you see here. And you can see down in here that the critical flaw in this fracture specimen was contained wholly within that one large grain that you can see here. I think a good example then of how this flaw contained within a large grain tells us something about the fracture behavior is easily demonstrated here. These were flexural specimens fractured of polycrystalline zinc selenide. And we measure the fracture strength of the material as a function of 1 over the square root of flaw size. If you recall the general expression for strength of brittle materials, this 2E gamma is related to the fracture toughness of the material, and A then is the flaw size. So if we measure the flaw size on the fracture surface, which is what we did, and plot then strength as 1 over the square root of flaw size, the slope of the curve, knowing the elastic modulus, should give you the fracture energy of the material or the fracture toughness, whichever way. And as it turns out, we can see from the data, here is all the fracture energy or the strength data, and you can see that it's pretty clear that the fracture energy required to grow that crack to cause failure was much more related to the single crystal value of 0.67 megapascals a meter to the 3/2 than to a polycrystalline value obtained on a large-scale crack in a fracture mechanics specimen. So that indicates to us that it's the local fracture toughness, not the macroscopic fracture toughness, that one must pay attention to in predicting failure. And again, the reason is that fracture began within that very large grain. And following on from that then, that one can see that then the fracture toughness, similar to what I showed earlier for R-curve behavior, increases as the flaw size to grain size ratio increases. So I go from single crystal behavior down in here, where flaws are just growing in single crystals of the zinc selenide, all the way up to polycrystalline material. But it took a lot of grains for the crack to grow through to reach this polycrystalline fracture energy or fracture toughness. And so if I'm predicting failure of material, I have to be very careful not to overestimate the fracture energy it will take to grow my flaw, which in turn will overestimate the strength at which this material should be operated. And zinc selenide isn't the only material that looks like this. There's work done on spinels and yttrium oxide, et cetera, that look exactly the same. So in other words, their fracture energies, fracture toughness range from single crystal values to polycrystalline values, and that transition can vary from one material to another, but it's behavior that we see frequently in many polycrystalline materials. And sort of schematically, what you're seeing here is that this would be a crack transitioning, that looks like, from purely growing as a smooth crack, relatively smooth crack in one large grain, to the point where it encounters many other grains that you see here, becomes a lot rougher, and so as I mentioned, there's usually a gradual transition in toughness. Now there's no evidence that cracks arrest at a boundary, so the fact that I get to a boundary doesn't mean, oh good, I'm safe, the crack will stop. We've never seen any data that suggests cracks stop once they start growing, so the strength of the material will be governed in this case by the material within that large grain, the fracture toughness of the large grain. And you see other evidence of this strength-grain size relations that's been looked at over many years, in which you see the effect that in small grains that the local microstructure controls. In large grains, it's the extent over which the crack grows in the microstructure that can make a much greater difference. So let me summarize a bit for this section, that there are a lot of toughening mechanisms available, but the toughness and strength are not necessarily proportional. You have to be very careful that if the flaws that causing failure are small, fracture can initiate within large grains, as we showed in zinc selenide, or even initiate in a range of grains which are not the same as the entire average microstructure of the material. And it's highly unlikely that the crack will stop just because it reaches that other section of large grain. So the point being is that ceramic microstructure is a key determinant of both fracture toughness and strength, and that grain size and grain distribution as well as crystal structure have to be considered, and that toughening can arise due to numbers of mechanisms but may not lead you to increased strength. So measuring macroscopic fracture toughness by some of the fracture mechanics techniques is useful, but one has to be cautious to predict increased strength just based on that. And then finally, I've left you with numbers of references to other key studies in the area of microstructural effects.